In a solution, current flows because the ions inside it move from one place to another. Bomb solutions conduct electricity very well, and some conduct poorly. Though the big question is, how do we actually measure this? First, resistance. Resistance with symbol A tells us how strongly a material opposes the flow of current. Its unit is the ohm. Resistance grows as the material gets longer, and it falls as the material gets thicker. Though resistance is proportional to length divided by area. We can write this fully as resistance equals ρ times length divided by area. Here ρ is the resistivity, which is the material's own property. Low conductance with symbol conductance is just the opposite of resistance. Conductance equals 1 divided by resistance. The unit of conductance is the Siemens, which is simply 1 divided by ohm. In the same way, conductivity kappa is 1 divided by rho. Its unit is Siemens per meter. When conductance equals kappa times area divided by length. Conductivity varies enormously from one material to another. Because of this, materials fall into three groups. Conductors like copper and silver, semiconductors like silicon, and insulators like glass and Teflon. There are two kinds of conductance. The first is metallic conductance, where electrons move through the metal and the metal itself stays unchanged. The second is electrolytic or ionic conductance, where the ions move through the solution to carry the current. Pure water has very few ions, so it barely conducts. Would add an electrolyte to it, and now it conducts well. Ionic conductivity depends on several things: the electrolyte used, the size of the ions, the concentration, and the temperature. Would measuring a solution has two problems. When direct current changes the solution itself. When 2, you cannot simply attach wires to a liquid. The fix is to use alternating current together with a special vessel called the conductivity cell. Inside this cell there are two platinized platinum electrodes, each of area V, separated by a distance L. For this cell we define the cell constant with symbol A star. The cell constant equals length divided by area, and it is fixed for a given cell. To find it, we fill the cell with a potassium chloride solution whose conductivity kappa is already known, and read the resistance. Then the cell constant equals kappa times resistance. Rearranging, conductivity kappa equals the cell constant divided by resistance. Modern meters read this conductivity directly. Wood conductivity depends on how many ions are present, so comparing two solutions by conductivity alone is not a fair comparison. Though we use molar conductivity with symbol lambda, molar conductivity equals kappa divided by concentration. It is the conductance per mole of electrolyte. Again, molar conductivity equals kappa divided by concentration. Its unit is Siemens meter squared per mole, and it can also be written as Siemens centimeter squared per mole. Step 1. Calibrate. Take 0.1 molar potassium chloride, whose conductivity kappa is 1.29, and read the resistance as 100. Hence the cell constant equals kappa times resistance, which is 129 per meter. Step 2. Measure 0.02 molar potassium chloride. Its resistance is 520. Go kappa equals the cell constant divided by resistance, that is 129 divided by 520, which is about 0.248 Siemens per meter. Step 3. The concentration is 20 moles per cubic meter. Go molar conductivity equals kappa divided by concentration, that is 0.248 divided by 20, which is 0.0124, 124 times 10 to the minus 4 Siemens meter squared per mole. Thanks for watching. Like and subscribe to Vidyarthi. Electrochemistry, last 12 chemistry in English.